Okay, got it. Welcome back, everyone. Here we are in the course on environmental bioethics within the Masters of Bioethics at St. Thomas University. Beginning always with a little prayer in the name of the Father, the Son, and the Holy Spirit. Come, Holy Spirit, fill the hearts of your faithful and enkindle in us the fire of your divine love. Amen. Okay, so this is our second lecture in this environmental bioethics course. And the first one was on the geosphere. We're looking at the various components of Earth for the possibility of life. So basically, we're looking at the abiotic factors, if you will, first, the non-biotic factors, the material presupposition for having life on Earth, beginning with the geosphere and the whole issue of the continents, the crust of the Earth, which is where life is happening, whether it's land or water. Now we're going to be looking at the atmosphere, the components of the atmosphere, which would be the gas component on top of the crust, all right, which has its own role to play, a critical role for maintaining life here on Earth. And then next week, we're going to be looking at the hydrosphere, in other words, the liquid component of Earth, the natural liquid component, which is going to be mostly the oceans, but also fresh water and brackish water. And then we're going to be looking at cycles in nature, in the environment, different cycles of elements and compounds that allow for life to occur. And then we'll move on to the human population on Earth and the bioethical issues that come up with that. So for now, we're still doing just basically Earth science right now, okay? Any questions or comments from the geosphere? Everyone did pretty well there with the summaries. I think it was pretty straightforward and pretty clear. The fact that our Earth has been around for about 4.5 billion years. Well, first of all, the entire universe has been estimated to be around for about close to 14 billion, rounded up to 14 billion years since the Big Bang, since the moment of singularity to this expanding universe, accelerating universe of full of galaxies and other massive bodies. Within galaxies are the planetary systems, and our planetary system has been dated to about 4.5 billion years, all right? So about 1/3 in the last 1/3 of the existence of the universe. And as a whole, this is more or less when galaxies arise in the model, in the expansion model of the universe. So here we are in this planetary system, in kind of in the middle of the inner orbits, with the smaller planets, inner planets, and the larger planets on the outer orbits of our planetary system. And the fact that the Earth is now cooled enough to have a solid crust, which is approximately 100 kilometers thick, where life actually exists, all right? Necessary for life, but not sufficient. We also need two other huge components of the surface of the Earth, namely the liquid component of water, and also the gas component, which we know as the atmosphere. So that's what we're going to be looking at today. And the atmosphere, within this context, I have to review a little bit the distinction between mass and weight, so that everybody is clear, because not all students in this program have necessarily a scientific or empirical background. It's a very varied background. And therefore, just to review the distinction between mass and weight, accounting for the gravitational pull. Then a little bit about fluid dynamics also, because the atmosphere is a fluid, all right? It's a gas fluid. So both liquids and gases are fluids, meaning that they flow and they don't have their own shape as solids do, but rather they take up the shape of the container. But an interesting question that we can ask, well, what is the shape of the container of the atmosphere if it's on the outside of a sphere, right? Okay, so we'll see how that comes about. Then the actual composition of air, the percentage of gases that are involved in making our atmosphere, the current atmosphere, because we also know that the atmosphere of Earth has changed at least 4 or 5 times that I've read, beginning with the primitive atmosphere that was very, very different from our current atmosphere and very toxic by the standard of life today, all right? We'll look also at stratification, the layers of the atmosphere, and then barometric pressure, because this is essential to understand patterns, weather patterns and climate, long-term climate, because of the big issue here, which is climate change, right? I want you to have a good grasp of weather and climate so that we can talk intelligibly about climate change and the anthropocentric or anthropogenic component of climate change. Anthropogenic meaning the human component of climate change. All right, so we'll look also at wind patterns for the establishment of weather and then eventually climate. And finally end with a natural right, a right to clean air. So let's go forward. First, this issue between weight and mass is important to understand because when we weigh ourselves on the scale, right, what that number that comes out, the 130 or 40 pounds that we all weigh, right, okay, or that we wish we weigh, those 140 pounds, that's not our weight. Scientifically. Our weight is actually 10 times more than that, all right? So if I'm weighing 140 pounds on the scale, my actual weight is about 1,400 newtons is the units. What the scale gives me is actually the mass, my mass. And so that is what is measured in pounds in the British system, or kilos or grams in the metric system, right? The metric system, the unit of weight, of mass, the unit of mass is the gram. And it's a very small amount, the gram. So to be useful for us in terms of this middle world that we live in, right? I remember what I talked about in the first course on the program of these 3 worlds that we live in simultaneously, the middle world that we can plainly experience with our senses, with our 5 external senses. And then there's the microscopic world, which by definition is smaller than we can see with our naked eye or estimate with our natural senses. We need instrumentation for that, namely the microscope of different kinds. That would be macroscopic world. And then there is the super macroscopic world, the huge world, essentially going beyond our Earth into the universe, the dimensions and occurrences of beginning with planetary systems and going forward into galaxies and the entire universe, etc. All right. For that, we also need instrumentation to get a grip on it and to measure it and study it. And those are the telescopes. So microscopes on the small scale, telescopes on the large scale, and just our 5 senses in the middle scale of where we live on a daily basis. We actually live on those 3 levels simultaneously, but we're normally just aware of the middle one, right? So anyway, when we measure ourselves on the scale, what we get is the mass, which again, in the British system, the unit is the pound, and it's non-decimal. That's why it's so confusing. whereas so smaller than the pound are the ounces, right, and so forth. But on the metric system, which is what is used as a convention for science, for empirical science throughout the world, it's the metric system. The unit is the gram, which is a very, very small amount. So 1,000 grams make up a kilogram. And just to have a rough proportion between the British and the metric system, 1 kilo is about how many pounds? It's about 2 pounds, 2.2 pounds, all right, 2.2 pounds. So 2 pounds approximately make 1 kilogram. And that's an easy translation there. Just like for the metric system for distance, right? The standard for distance in the metric system is the meter, 100 centimeters, right? And in the British system, it is not the meter, it is the foot. So about 3 feet make up 1 meter. So, and 3 feet we know is a yard. So about a yard in the British system is about a meter in the metric system, okay? If we bump it up to the kilometer, right, or kilometer, it's about 1.6 kilometers make a mile. And so about 1.5 kilometers, more or less, make a mile, just for some easy conversions. Okay, well, let's leave it at that for now. Temperature is another one that we can talk about later, maybe when we talk about the hydrosphere for conversions. At any rate, so when we weigh ourselves on the scale, we get our mass, which is either pounds in the British system or kilograms in the metric system, all right? If we wanted to know our weight is actually our mass multiplied times gravity, which is a force of attraction, as we know, one of the 4 fundamental forces, right? Also known as a field together with electromagnetism, the 2 fields, and then the other 2 of the fundamental forces, to recall, are at the super macroscopic level, the strong force and the weak force at the atomic level. All right, so, and those are also known as attractions. At any rate, when we multiply the mass times gravity, then we get our true weight. And so whereas our mass remains constant in different planets, for example, or in different planetary systems, our weight will change according to what planet we're at or where we are at on the planet because of gravity. And we know that gravity dissipates from its origin out to the periphery of whatever sphere, whatever massive body is exerting the gravity, okay? Again, to recall a little bit more on gravity, it is the name for this force that really every body exerts some gravity. Every body exerts some gravity, what we call massive body. Now, a massive body doesn't have to be huge. Our bodies, you and I, all right, are massive bodies because we have mass. It doesn't mean that we're huge, all right? The Earth is also a massive body, and so is the sun, but so is this marker. I don't know if the camera is, you can see it with the tiles reduced, but I'm holding a marker, a magic marker on my hand. This is technically also a massive body, not because it's huge, but because it has mass. And so every massive body down to the molecular level exerts gravity, but it's in proportion to the mass, so that the more massive a body is, the more dense rather a body is, the more gravity it exerts, okay? And so whereas we do exert an attraction amongst each other, and that's not just figuratively, you know, we say, well, there's an attraction between those people. That's not just figuratively as a figure of speech. It's literally, there's an attraction between every person on Earth, and the closer they're to each other, the greater the attraction literally at a physical level because of the gravity that their bodies are exerting on each other. However, that type of attraction, gravitationally speaking, physically speaking, is negligible, is totally negligible compared to the attraction that the Earth is exercising on our bodies, right? That the mass of the Earth is exercising on our mass of the body, namely the gravitational pull. And that is essentially what is keeping us grounded, literally, again, physically grounded here on Earth. And that's why we can walk, let's say, around the Earth without walking out of the Earth and into space. I remember way back, because I'm that ancient that I was a teenager about 50 years ago in the 1960s, when Neil Armstrong was landing on the moon, the first person, the first man on the moon, right? It was in the 1960s, and I remember clearly being in Mexico City as a teenager with other friends, enthralled, watching on a TV, a brand new Technicolor TV back then. This was the latest thing in the 60s, was color TV. All right, and it was this brand thing called Technicolor. Anyway, we were watching Neil Armstrong putting his foot on the moon and transmitting through Houston Space Center. One small step for man, one large step for mankind. You hear the static and so forth, that he's putting his foot on the moon, right? Well, I remember that time that the astronauts, I mean, there was so much stuff of space travel being pumped in the regular media because there was also the space race with the Soviet Union back then and all that. And anyway, one of the details that I still remember from 50 years ago was that they had to be careful when they actually landed on the moon and got out of the spaceship onto the surface of the moon, not to get too excited. And they could jump. They were given permission to jump up and down, but very, very little, just barely, you know, just raise their feet off the ground and come back down. In fact, I also remember, now it's coming back, their boots where they had lead on the sole of the boot, if I recall correctly, to ground them a little bit more, to make them a little heavier, okay? Why? Because the mass of the moon is obviously much smaller than the Earth, so the gravitational pull on the moon is much less than the Earth. And I remember the commentators mentioning back then that if a person on the moon just jumped up away from the moon very strongly, jumped off the moon, of the surface, they could literally jump off into orbit. I don't know if it's true or not, but I remember that being put out by media back then, just to make the point that they had to be very, very careful about moving around on the moon so that they wouldn't fly off, okay? I don't know if it's true or not, but that's what was being said back then. Anyway, just to emphasize that way, whereas mass stays constant because it's the actual measurement of our body mass, okay, of our bodies in grams or kilograms. The weight is the mass times the gravity, taking into account the gravitational pull of whatever massive body we happen to be on, which for the vast majority of us, it's planet Earth, which means also that as we go away from the surface of the Earth, that gravitational pull changes. You see, it changes. And this is Newton's famous discovery, right? About the law of gravity. He actually got to quantify it. And this is the quantification. It's an acceleration, because since it's a pull toward the center of the Earth, all right? And we understand that physically we cannot get to that center of the Earth because we'd have to go through the crust, through the mantle, and through the core, but the pull is there. And he estimated that gravitational pull to be this type of acceleration, all right? 9.8 meters per second square. Because it is an acceleration, then the seconds are squared. And that's what makes it an acceleration. But the fact that it is this quantity, all right, and this constant, then it is a constant acceleration and not a varied acceleration, right? A constant acceleration would be if we get on the expressway and we press on the accelerator at a constant rate. We press on that accelerator. A non-constant acceleration would be if we press and release the accelerator, press and release the accelerator, or press and release the brakes, right? The car is going to change in acceleration and deceleration as we do that. So this is a constant acceleration, 9.8 meters per second square. We can round it off for the purpose of argument to almost 10 meters per second square, all right? It's pretty fast, 10 meters per second square. And that's why also it's very dangerous and illegal and unethical to throw stuff out of buildings because it accelerates as that stuff is going down. For example, if you throw a penny from the top of the Empire State Building, by the time that penny hits the ground, it is moving practically at the speed of a bullet because it is accelerating as it is going down. Of course, there is also friction, and given that the penny is flat, it will probably go at its edge like that, right? The edge of least resistance, surface of least resistance, but it is accelerating as it is going down. It is not just coming down at the same rate, at the same speed, okay? And so that's an acceleration, which also means that the opposite argument works. As we move away from the surface of the Earth, that gravitational pull is less and less and less until that pull itself becomes negligible, and we essentially go into space where the gravitational pull of the Earth is negligible. But then we are also engaged in other gravitational pulls, significantly the pull of the sun and so forth, and then other planets also exert gravitational pull among each other, all the planets, depending on how large or small they are and depending on where the orbits are, because the orbits are not circular but elliptical, right? Which means that sometimes the planets are closer to each other than others, and all that has an influence on gravitational pull, mutual gravitational pull, so on and so forth. Okay, so I think that you should be sufficiently cleared and tired about the distinction between mass and weight. When we're weighing things on Earth, we're actually getting their mass. If we wanted the actual weight, we will have to multiply it by the gravitational constant of 9.8 meters per second square. And then the units are Newton units in honor to Isaac Newton, who discovered it. All right, now let's look at some fluid properties, because I was mentioning at the beginning of the lecture that the atmosphere is also a fluid. Gases are fluids, just like liquids are fluids, right? It's just that gases are much thinner fluids. They're not as dense as liquid, and therefore we normally don't see them unless it's a color gas, but they are flowing. And a very simple, easy experiment, if we move our hands fast through in front of our faces, if we move our arms fast from one side to the other, we will feel some wind through the palm of the hand. If we're moving forward from one side of the arm to the other side, we feel a little bit of a breeze on our palm. If we move in the opposite direction, if we move the arm fast in the opposite direction, we will feel that breeze on the back of our hands, right? Especially the hairs. And so that breeze that we're feeling is, or that wind is actually that we're going through the fluid, and the fluid is offering some resistance, but very light resistance because, again, the atmosphere as a gas is a light, it's not as dense. But it is a gas, it does have volume, and it's made up of atoms and molecules, all right? And therefore, it is also subject to gravity. The atmosphere is subject to gravity, and that is essentially what is keeping the atmosphere in place, meaning around, like a shell around the Earth. It is the gravitational pull on the atoms and molecules that form the atmosphere. Yes, the gas is being held in place by the gravitational pull, all right? But it's also a dynamic fluid situation, mostly because of temperature and pressure, and that the fluid then is moving somewhat up and down and mixing around, also because the Earth is rotating, which also is exerting a certain spin on the atmosphere. And so let's take a look at all that one step at a time. Some properties then of fluids is that they take up the volume of the container. However, there's a difference here between liquid and gas. I'll get to it in a minute. Just let me cover the second property here of fluids is that they expand or contract with heat and or pressure, all right? So solids also expand or contract with heat and or pressure, but not in a measure, not in a easily detectable way with our common senses. Generally, even though solids also expand and contract, right? For example, one time I had someone tell me that this issue of metal fatigue, some planes at one point, some airplanes at one point were losing parts of their wings and their rudders and so forth several years back. And engineers at first couldn't figure out what was going on. And then when exam was done, rigorous examination was done on those parts that were, came off the plane in flight, right? They realized that there were cracks, there were microscopic hairline cracks on the metal of the airplane, which are alloys, very sophisticated alloys that have properties. For example, they're very strong and at the same time they're very light and so forth. Anyway, they found these tiny, tiny microscopic hairline fractures, and they realized that it's what they call metal fatigue. In other words, an airplane may stretch or contract about a foot from being on the ground or being in flight 30,000 feet above the atmosphere, all right, above sea level. So the metal actually expands or contracts on the airplane. And at first, engineers had not realized that. And that slight but real expansion and contraction, and I mean a foot is detectable, right? It's just that we cannot observe it going into 3,000 feet into the stratosphere. But that expansion and contraction over many hundreds or maybe thousands of landings and takeoffs actually is fatiguing the metal, is tiring out the metal so that the metal will eventually develop a microscopic or hairline fracture. And then that over time, that fracture can actually break off, right? So anyway, what I'm trying to say is that solids also expand and contract with heat and or pressure, but much less visible or much less visibly or drastically than fluids, all right, that liquids and gases. So liquids and gases expand or contract significantly with heat and or pressure. Now, the two types of fluids then are liquids or gases. And in the natural world, the atmosphere will be gas, whereas the hydrosphere will be the liquid component of Earth, but vast majority of which is obviously the oceans. Now, I also want to say that there's a little bit of a difference between these two fluids. So liquids, because liquids are much more dense than gases, they are more reactive, if you will, to gravity. And so liquids do take up the volume of the container, right? They don't have a shape of their own like solids do. But in liquids, liquids only take up the bottom part of the container. They only take up the shape of the bottom part of the container, right? For liquids. Whereas for gases, let's say in an enclosed area, a gas will typically take up the full volume of the container, not just the bottom part of the container as liquids, but the full volume of the container, all right? So for example, the atmosphere inside this room right now, the air inside this classroom, all of the molecules are essentially flying around randomly, bouncing against each other, bouncing against the walls and so forth. Some of them actually going through the wall at the super microscopic level. And therefore, there's a random motion of the gas of the air inside this room right now. Different it would be if we fill this air with liquid. Well, it would only take up the bottom part of the room, okay? The shape. All right, let's move forward. Another, some terminology here to understand. Matter, we'll be talking matter and energy and the conversion between both with Einstein's equation. But matter basically in physics and in the natural world, we can talk about pure substances or mixtures, all right? So all matter can be subdivided into these two large categories, pure substances or mixtures, all right? And then pure substances are either elements or compounds. Elements is, for example, the periodic table of the elements, the 300 or whatever elements that we have, some natural, some created in the lab and unstable, but the number of elements in the periodic table, those are the distinct elements. And what is the difference between one element or another is simply the number of protons in the nucleus, the number of protons, all right? So as we add one more proton to that nucleus, we go from the smallest element, which is going to be hydrogen, all the way up the scale to the largest one, which I really don't know what it is, but 100, 200, whatever protons have been, humans have managed to bombard into that nucleus to make these artificial, unstable elements, all right? So those are elements with single, with individual number of protons and just one element of its kind. But when we have two or more elements combined in what we call molecules, then those are compounds. So molecules by definition are compounds because they are two or more elements combined. Two or more different elements, as for example, water, two hydrogens, one oxygen. On the mixture side, then it's more heterogeneous, if you will, more mixed. The compounds, it's, if you will, combinations between compounds and elements shown here. If the mixture is even, let's say, even mixture of compounds and elements, then that's called a homogeneous mixture. Typically, gases will be homogeneous mixtures, whereas is the mixture, the compounds and elements within that mixture are separating, right? As example, a suspension, not a solution, but a suspension. For example, putting sand into water shake up the container, and for a while the sand will be suspended in the water column, but after a while the sand will settle to the bottom, all right? That's what we call a suspension as opposed to a solution. That would be a heterogeneous mixture. So a solution could be homogeneous mixture, whereas a suspension will be a heterogeneous mixture for chemical purposes. Our atmosphere basically is a solution or a homogeneous mixture. Okay? But depends on the layer we're at. Depends on the layer because it does stratify as we go through the layers of the atmosphere. We'll get to the layers in a minute. Let's look at the chemical composition of the atmosphere. In other words, the gases that make up the atmosphere, all right? Which are, they typically occur either as single atoms or in a diatomic fashion. In diatomic fashion means that there will be two atoms of the same element linked together, stabilizing their outer orbits essentially, all right? So it makes them stable. And that's the case with nitrogen, for example, which is the largest component of the atmosphere. Almost 80% of the air right now in this room and in the atmosphere, almost 80% is nitrogen, and it's diatomic. In other words, N2, N for nitrogen, and the subscript 2, meaning that there are two atoms, all right? It's called diatomic, D-I-atomic, diatomic. So almost 80% of the atmosphere is nitrogen. And the other 20% approximately is oxygen, all right? Which is also diatomic, O2, all right? And then the other 2 or 1%, the other 1% that is left here approximately, because these are approximate numbers, they're rounded up to the nearest whole number, all right? These are rounded up to the nearest whole number. There's about 1.5% left, or almost 2% left. Almost 1% of that is argon, AR, which I understand is not diatomic, but it's by itself, just atomic argon, which on the periodic table is AR, all right? Again, inert argon gas, almost 1%, not quite 1%. And the other 0.9% that is left, right, is other gases that are called trace elements or trace gases. Actually, they're not real, not all of them are elements because CO2, significantly, CO2 is also technically a trace gas, but it's not an element because it is made up of two elements, right? Carbon dioxide, it's carbon and oxygen, and therefore it's a molecule made up of, it's a compound made up of two elements, carbon and oxygen. So CO2 is one of those trace gases. The other trace gases are neon, helium, methane, which is also a compound, nitrous oxide, also a compound, and ozone, which is O3, is oxygen, triatomic oxygen, okay? Now, significantly, I want to zero in a little bit on CO2 for a moment, carbon dioxide. We have heard a lot about CO2 in the past years and decades, increasing alarm of the rise of CO2. Look at the normal component of CO2 in the atmosphere is not even, is much less than 1%, is much less than 0.1%, all right? It's 0.04%, 0.04%. So 4 centesimals of a percentage, right? 4 centesimals. And that is also translated into another unit that is easier to deal with, which is called parts per million. So when we do the arithmetic of translating 0.04%, all right, into parts per million, we come up with 400 parts per million. Okay, just hold on to that for a moment. I'll break it up in a minute. But so this is the natural percentage of CO2 in the atmosphere, in the air that we are breathing right now, is 0.04%. And even that is a high rate that has been increasing steadily for the past, well, half century very fast, and about 250 to 300 years increasing because of the Industrial Revolution. I'll get there in a minute. I want to go back to nitrogen for a moment, because since the vast majority of the air that we're breathing right now is nitrogen and not oxygen, only 20% is oxygen, only about 1/5 is oxygen, but the other 4/5 of the air that we're breathing is nitrogen. Does it have an effect? What does it do? It does nothing. It's what is called an inert gas, inert. It comes in and out of the lungs, and as long as it stays in gas form, right, it doesn't go into the system. It's not absorbed by the alveoli in our lungs. Different from oxygen that is absorbed to a certain percentage. We don't even use the 20% of the oxygen that's in the air that we breathe, all right? We use a small percentage of that, but that is absorbed in through the alveoli, and in exchange, we exhale out CO2 because of cellular metabolism, cellular respiration, right? Which burns up oxygen and releases CO2. So that gas exchange goes on in the lungs, and that's the way it is. All right, so let me move now into this CO2 for a moment. Another little slide here, drilling in for a moment. I want to explain this ppm and ppte first. ppte, which means part per thousand. You'll see that in the literature and so forth, especially when referring to gases and natural gases or artificial gases pumped into the atmosphere. Okay, it's a very common unit that is used for measuring gases in the atmosphere, ppte or ppm. It's also used for measuring salt in the ocean, for example, and we'll get to that next week. So for now, ppte, for example, it means, it's an acronym for parts per thousand, ppt, all right? Just very simply, we are 6 persons now. We are 6 persons in this course, right? 5 of you watching the lecture and myself talking away. So we are 6, right? So we're 6 persons. If we were hypothetically in a group of 1,000 people, we would be, our density would be 6 ppt, 6 parts per 1,000, all right? And the other component of the 1,000, the other people, will be the 994 other people who are not us in this course. So you get it? So we would be 6, our density would be 6 ppt in a group of 1,000 people, right? All right. So we can make the same argument. If we were in 1,000,000 people, we would be 6 ppm. We would be 6 parts per million. That would be our density among 1,000,000 people, all right? And the other 999,994 people will be not in this class. All right. All right, so PPT, ppm, it's a measure of density that is used commonly for measuring amounts of different gases in the atmosphere. And I was mentioning that when we translate that 0.04% of CO2 component in the atmosphere, translated into ppm, comes out to 400 ppm, all right? Now, this is the level that that CO2 obtained. This is the density that CO2 obtained in the atmosphere in 2013. 2013, about 8 years ago, okay? 8 years ago, for the first time, In the recent history, since our current atmosphere, remember how I mentioned at the beginning of class that our atmosphere has undergone drastic change, significant drastic change in the gas composition, at least 4 or 5 times since the primitive atmosphere of early Earth, which was extremely toxic to us, you know, much higher methane, much higher CO2, much higher hydrogen, et cetera, and much less oxygen, almost no oxygen back then. Well, that atmosphere has changed about 4 times to what we have the current atmosphere, which I don't know how long it's been around, but it's been around at least hundreds of thousands of years, if not actually millions. No, actually millions of years. Why? Because we have had life on Earth for millions of years. So actually just thinking out loud here for a little bit, the ones who essentially made our current atmosphere, particularly the oxygen component of it, and also reducing significantly the CO2 component of it, were the cyanobacteria, which appeared on Earth close to around 3.8 billion years ago, close to 4 billion, all right? And so we've had a current atmosphere for at least 3 billion, if almost close to 4 billion years, of the 4.5 billion years that we have been in existence. So again, just thinking out loud with you right now, we can say that the other 3 atmospheres that were so significantly different from ours today occur only in the first half billion years of Earth. All right, going forward now, back to our current atmosphere. For the first time, that 400 parts per million was achieved. The density of CO2 happened in 2013, okay, which is here. Now, in 1950, it surpassed the 300 parts per million. So the scale here on the y-axis, the vertical scale, it's parts per million, as you can see. Carbon dioxide level, you can interpret this also as density, right? The density of CO2 in the atmosphere. The low end here is 160 parts per million, and the high end is 480. So there's a range here of about 600 ppm. The range is about 300 ppm, okay? In fractions of about 20. And here is the 300 ppm, about halfway on the graph, halfway. Why 300? Because it's the highest peak of this interglacial period. These are glacial and interglacial periods here, okay? So when the CO2 has been lowest, it correlates with low temperature of the Earth. And when CO2 has been highest, it correlates with high temperature of the atmosphere of the Earth, because CO2 is a greenhouse gas. Greenhouse gas, it retains heat. CO2 retains heat, like methane retains heat, like water retains heat, all right? And so when there's a higher concentration of CO2 in the atmosphere, it correlates with a tropicalization of the Earth, a warmer surface of the Earth, okay? And conversely, when there's low CO2, then it's a winterization, a low temperature of the Earth. At any rate, the 300 threshold is there in one of the tropicalizations about 3 ice ages back, 3 tropicalizations back. That threshold, right, which has been going on almost 1 billion years, that threshold was surpassed back in 1950, 70 years ago already. And it has continued to rise exponentially, almost vertically since then, shot up tremendously in the past 70 years, CO2. And this is what is known as the anthropogenic effect, all right? That this is caused mostly through industrialization, mostly through burning, and the major culprit, of course, is going to be fossil fuels. So since the 1950s, the burning of fossil fuels has skyrocketed to increase the amount of CO2 in the atmosphere to the current 400 ppm, all right? And that's why the climate accord, the Paris climate accord, and so forth, and trying to get back to that accord is very controversial, it's very political, it has all kinds of impact on industry and society and lifestyles and everything else. We'll get to it toward the latter part of the course itself. But I just want to introduce that thing now, that already 400 ppm is an alarming rate of CO2. The Earth has never been in at that height since there has been life on Earth. It's another way of putting it, all right? Okay, I'm gonna leave it there for now. We'll get to that analysis later as we look at the human component of environmental bioethics. Let me move forward back to the atmosphere itself and the physics of the atmosphere. So there are these layers of the atmosphere, because again, different elements and compounds are reacting differently to the gravitational pull. And the bottom line is that there are now 5 more or less stable layers to the Earth's atmosphere, okay? Each planet will have its own atmospheric component and its own layering and so forth, according to many different dynamics that are occurring in other planets, and the gas composition and the percentage of that, and the gravitational pull that those planets are exerting on their own atmosphere. But back to planet Earth, we have these 5 layers, beginning with, maybe this should be reversed, I don't know. The point is that this is the one closest to the surface of the Earth, all right? And we go outward from the surface going down here. So maybe I should reverse these if this, so the surface of the Earth is up here. We go through the troposphere first, then stratosphere, mesosphere in the middle, thermosphere, there's a thermocline there that the temperature changes drastically, and then finally the exosphere, which is the outer layer already connecting us out into space. Let's look at this graphically. Here are the layers. Here's the troposphere close to the Earth. Closest to the Earth is where life is occurring, and also navigation through the troposphere by flight, whether it's airplanes or balloons and all that. All the flight that we do is essentially here in the troposphere, all right? Except when we are reaching out into space, of course, we have to go through the other layers into eventually to the exosphere. And satellites are, I don't know exactly where the satellites are really, but there are different layers up here to not interfere with the flight of the troposphere. In between each layer is what is called a pause, P-A-U-S-E, a pause. So between the troposphere and the stratosphere is a tropopause, all right, tropopause. And so the pause will take the name, the prefix of the previous layer. Therefore, the layer between the troposphere and the stratosphere is going to be the tropopause. And then the intermediate layer, the transition between the stratosphere and the mesosphere, is going to be the stratopause. Same argument between mesosphere and thermosphere, mesopause. And finally, going out into, there is no thermopause as such, all right? It's just a gradual diffusion from the thermosphere out into the exosphere. Technically, the exosphere is actually the rest of the universe. So there is no thermal pause there. It's just a very gradual diffusion of density here. There's another phenomenon that occurs through these layers, and especially here between the thermosphere and the exosphere. I'll point it out in a minute. So again, 5 layers to go from the surface of the Earth out into space. All right, Let's look a little bit at temperature and distance. First, the distance. The troposphere, which is the thinnest of the five, is approximately 11 kilometers or 10 kilometers, if you want to round it up. It's about 10 kilometers above the surface of the Earth, all right? 10 kilometers approximately. And then the stratosphere is about 50 kilometers. The mesosphere is about 87, okay, about 90 kilometers, almost 100. And then the thermosphere, which is the longest, right? The thickest, if you will, not by density, but thickest in depth or altitude. Altitude is the proper word. About over 400 kilometers up to 500 kilometers from the surface of the Earth. All right, so this is distance from the surface. 10 kilometers, approximately rounding off for the troposphere, 50 for the stratosphere, almost 100 for the mesosphere, and then about 500 for the thermosphere. And then that final transition layer of the exosphere. This also is where the transition between the thermosphere and the exosphere, all right, is also known as, this is where atmospheric escape occurs. Atmospheric escape, what is this? These are the matter, the atoms that are escaping the Earth. Not only gas, all right, but other molecules, other atoms and molecules, little by little, make their way out through diffusion, all right, against gravity, out into space. Over relatively long periods of time, they make their way out. And so we are gradually but surely losing material, losing matter from Earth at a very, very tiny rate on a small scale, but when we put it in terms of billions of years, significant amount of material has left the Earth, and that is known as the atmospheric escape, all right? Of course, it is a dynamic system because since the Earth is moving through a planetary system in around the sun, and it's also moving through space, the planetary system as a whole, and the galaxy of Milky Way as a whole, also moving through space. We're also picking up matter from outer space into Earth, which again, at a daily scale or even a day or yearly scale is insignificant, but when you bump it up to billions of years, is definitely significant. Again, I remember back in the 70s when I was teaching high school biology at San Bernard High as Mr. Chofi before the priesthood. I remember there was an article that appeared, some fellow who was proposing that the water, the H2O molecules on Earth, so he had made some kind of calculation that the amount of water that we have on Earth is larger than the water that would have been produced naturally by the natural combination of hydrogen and oxygen, okay? So in other words, the primitive Earth did not have enough hydrogen and oxygen to account for the amount of water that we have on Earth today. And that has been a quandary for many, many decades, had been, until this fellow proposed that that is because a significant amount of the water that we have on Earth actually comes from space. We didn't produce it ourselves, or the Earth didn't produce it itself by hydrolysis of mixing water, mixing hydrogen and oxygen, but rather we picked it up from space, literally like a huge sponge that is moving through space and picking up water molecules, all right? And I remember at first this fellow was laughed at, you gotta be kidding, this is totally science fiction, but yet I think that now it has been proven that that is actually true, that we have essentially picked up the bulk of our water on Earth from outer space, okay? So just as we're giving off matter into space, we're also picking up a lot of stuff from outer space over long period of time, right? That scale is in at least in millions of years, if not billions of years, which remember for the American billion, it is 1,000 million, all right? So an incredibly large amount of time. All right, then with regards to the temperature itself, this is measured in degrees centigrade. So here is 0, all right? This is below 0 in centigrade. So this is freezing. This would be water in this state would be solid, right? And from 0 above here, the scale actually only goes to about 80 because I see 20, 40, 60. So this would be 80 degrees centigrade. So this would be liquid. And then above that would be gas just by temperature. But we can also achieve a similar effect by pressure or less pressure. If instead of adding temperature to water, we release pressure from to water, we put that water into a lighter pressure, then water will go into the gas state. And that's actually what happens with clouds, and is that it's colder up there, right? So just by temperature alone, that water in the atmosphere should be at least liquid, if not solid, and yet it's gas. Why? Because there is less pressure. In other words, it's further away from the surface and therefore less gravitational pull and less atmosphere also above it, so that there is less pressure. And that's what causes the pressure. Is actually the atmosphere weighing down, on the surface of the Earth. So yes, newtons. So the pressure of the Earth, pounds per square inch, okay, is a measure of pressure. It is the weight of the atmosphere. In other words, its mass times its gravitational pull, all right, toward the center of the Earth. But of course, it's not going through the crust because it's gas. All right, so anyway, in the troposphere is also when we have the weather systems, okay? And there's a gradual but pretty inclined drop in temperature as we rise on the atmosphere. Through the troposphere, there's a fast decline in temperature, right? Till we get to the tropopause, going into the stratosphere. And into the stratosphere, the temperature actually rises because we are going away from this density, right? It's becoming much less dense, much fewer molecules up here. And therefore, the temperature rises again of the stratosphere. The temperature rises to around 0. And when we make the transition from the stratosphere into the mesosphere, again, because of the distance, mostly the distance to the surface of the Earth, and now this atmosphere is being influenced less and less by the gravitational pull than by other forces that are out in the universe. So there's again a drop in temperature, significant, down to minus 80, around there, all right, close to minus 100. So water at this stage normally would be frozen. But the molecules, there is water vapor up here, but the molecules are so separated from each other that they will very, very seldom encounter each other to interact into either liquid or solid, all right? So they essentially remain as a gaseous state together with any other elements or compounds that are in this upper atmosphere here. So finally, we get to the thermosphere, where the temperature will again rise very, very fast and very steeply into the very high temperatures of the atmosphere, of the exosphere, of space, actually, where there is essentially nothing to hinder the temperature up there. Okay, so there's this gradual zigzagging of the temperature of the atmosphere as that the thermometer goes through different layers of the atmosphere. So you can see again, it's a dynamic system, but the bulk of our weather happens in this region here between the troposphere and the stratosphere. All right, that's the bulk of the weather on Earth. Moving forward, these are different types of clouds shown here. Mostly the cloud formation occur in the, as I mentioned, in the troposphere, the upper 10 kilometers more or less of the atmosphere. Here's the decline in temperature going from, well, it has it around 20 degrees centigrade. 20 to 30 is more or less the range in centigrade. Above zero, right? It's the temperature of the atmosphere that we feel on the surface. But as we go up, that temperature drops. Again, there's less density. And so we get different cloud formations, lower clouds, especially above the ocean that we can see just looking off to the east. Typically, if you want to know where the east is, just look up at the sky. And when you see the large white cloud formation in as a, almost like a river of clouds, all right, a whole range or if you will, a mountain range of clouds along the horizon. Typically, that will be the East Coast. That cloud formation typically is above the Gulf Stream. Above the Gulf Stream, anywhere from 1 to 5 to 10 miles offshore from the East Coast, going right up the coast of the Florida coast, the Florida East Coast. There is above it, above the Gulf Stream, there is a current of clouds moving with it, all right? And then when those clouds move into shore, typically they condense and then they precipitate into the tropical rainstorms that we get usually in the summertime and so forth. As that air continues to go up a mountain, it will cool again and cause more precipitation on the windward side of the mountain. And once it goes over the peak of the mountains, then that mountain range essentially has combed out, has pulled out the humidity of the air so that on the other side of that mountain range, it will be a desert type because that air will now be dry, not humid, okay? What is known as the leeward side, the windward side where the winds are blowing into the mountain, and the other side is called the leeward, L-E-E-E, ward side of the mountain, when the wind is moving away from the mountain range. Okay, let's move forward. Let's look at now the pressure, the barometric pressure. The barometer is what measures the pressure because it's a reference to the way this pressure is measuring, which is the downward force of the atmosphere. That's the pressure that we're talking about. The pressure that we feel, we don't actually feel it that much because we're born and live all our lives on the surface of the earth, all right? But if we go out into the upper layers of the atmosphere, that atmosphere is getting much thinner and thinner and thinner. And so literally we would tend to explode. If we put a balloon out into the atmosphere, right, that balloon will continue to expand. The molecules inside will expand until it actually explodes out. Conversely, if we fill the balloon at the higher levels of the atmosphere and bring it down to Earth, that balloon will contract and compress and compress and compress in because of the weight of the atmosphere on the gas inside the balloon, okay? And so what we have on the surface of the Earth is what is known as 1 atmosphere of pressure, 1 atmosphere of pressure, which is also known as STP, standard temperature and pressure, STP. So STP is 1 atmosphere of pressure at the temperature of whatever temperature it is, typically between 20 and 30 degrees centigrades at sea level, all right? If we go up a mountain, that STP, that temperature and pressure changes. But At the surface of the Earth, actually surface of the ocean, it is known as 1 STP, 1 atmosphere of temperature and pressure, which is known as the standard STP. So sometimes people talk about 2 atmospheres, 3 atmospheres of pressure, etc. Okay, back to the pressure itself, because this is also what influences our weather, the weather system. And the accumulation of weather over a long period of time is what is going to give us eventually the climate, all right? But weather is on a daily basis, on an hourly basis, daily, weekly, monthly, yearly basis. Even up to decades is still basically weather, all right? And then over a long period of time, we get into what we know as climate and trends. So let's look at the barometric pressure. How is the barometric pressure measured? We measure it by this scale, the scale of inches of Hg. Everybody know what Hg is? I think it's hygronium. It comes from the Latin hygronium, which means mercury, all right? Just like sodium is Na, sodium on the periodic table of elements is Na because sodium in Latin is called natrium. And so Na, all right? And mercury in Latin is called hygronium, so that's why we get Hg. So In represents inches and Hg represents mercury, so 29.92 inches of mercury. That's what I'm calling the magic number to establish the atmospheric pressure. Atmospheric pressure, 29.92 inches of mercury. Yes, on a column that has mercury inside and then is open at some point to feel the pressure of the atmosphere on that tube, right? And so that is called a barometer. It measures atmospheric pressure. And the standard pressure that I was mentioning, standard pressure, STP, standard pressure and temperature, is 1 atmosphere is equal to 29.92 inches of mercury on that little tube, right? Okay, well, here is a little video. Take a break for my talking. Here's a little video on how the barometer works by some young lad who is going to explain it to us. Here we go.
Would you have used Roundup Weed Killer if you had known that it would be linked to over...
Okay.
Well, today we're talking about understanding.
Hold it. No need to yell here. Okay, so let's bring this down a little bit. And let's make this full screen. All right, so here's a young fellow. It looks like a fall out there because all the trees, all the leaves have fallen, right? And the sky is gray and so on and so forth. Remember Peter, Paul, and Mary, or Mamas and the Papas? That was a song from way back last century. All the leaves are brown and the sky is gray. Well, the sky is blue here, but it certainly looks like fall. And this fellow is going to tell us how the barometer works. Go.
Talking about understanding barometer ratings. And what we use to measure the air pressure is called a barometer. And essentially all air pressure is the downward force of the atmosphere. And when you have more downward force, the air pressure rises. When you have less downward force or less weight, the air pressure drops. And that's important because typically what happens is when the air pressure is rising, the air is sinking, it's putting more pressure on the earth. But even more importantly, sinking air clears out the skies. So generally you have nice weather when the skies are clear and the barometric pressure is high. When the barometric pressure falls, you have rising air. It's rising away from the surface of the earth. So the pressure that it's putting on the earth goes down, the pressure falls. And typically with low pressure, you have clouds, you have rain, and when you have extreme conditions, you can also have thunderstorms, sometimes severe. The lower the pressure drops, you also get the worst weather. For instance, the lower the pressure in a hurricane, the stronger the hurricane is. So understanding how to measure it, we use these barometers. And it's very simple to read a barometer to tell you if the weather's going to turn good or bad, or whether you have high pressure or low pressure. Standard pressure, here the average pressure is 29.92 inches of mercury. That's the way we measure it. That's the way it's marked out on most barometers, whether it's a mercury barometer, a water barometer, or an aneroid barometer. This type is an aneroid barometer. When the pressure rises, the needle goes up. And if you measure it against 29.92, anything above 29.92 is considered high. The closer you get to 30 or 31, considered high. And the farther below 29.92 you go, the closer to 29 or even below 29, that means the pressure is low. So simply watch it, engage it against that 29.92 inches of mercury. Above it is high, below it generally is considered low. If you're learning this Our Lady.
Okay, give me a minute, getting back to the presentation, right? So you see the magic number, right? It's almost 30 millimeter or inches of mercury, but not quite. And when it's above it, then it's high pressure. When it's below it, it's low pressure. And one thing that is not too clear, why is it that high pressure, so we can understand if there's high pressure, it moves the clouds out of the way. Think of it that way. When there's high pressure, if we put high pressure here, it's going to displace this cloud formation. It's going to move it away from where the pressure is being exerted. But what happens with low pressure is that the surrounding weather moves in. That's something that he didn't mention, which in my opinion would have been useful. We'll see that further on in the second part of the lecture as we talk about the wind patterns. But basically, when there is low pressure, right, what happens is the weather from the surrounding environment moves in. By weather, I mean the cloud formation or the humidity from the surrounding environment, from the surrounding troposphere moves in to fill in that low pressure. You follow? And so it's drawn in. In a drastic example, the most dramatic example of that is actually, like he mentioned, a hurricane. A hurricane has such low pressure at the center, at the eye, that is drawing in everything else. And that's also why you see that circular motion of the hurricane photographed from above, because it's drawing in everything that's around it. All the weather that is around it, all the humidity that is around it. And that's going to bring, of course, rain and precipitation and very high winds because of the vortex that is formed in trying to fill into that void, that low pressure system that has been generated, okay? All right, so what happens now? What happens now is that we're going to take a break because I'm going to shift gears a little bit and talk about how the Earth heats up and what is it that is causing the heating of the Earth. But in order to understand that argument, I need you folks to clear up your mind a little bit. And we need to talk about some distance and relative distance of the Earth to the sun and so forth. So why don't we take 5 minutes here? It's 10:55 according to my clock on the computer. So I'm going to take 5 minutes, all right? And be back by 11. We'll continue the presentation. Now, before leaving, any questions or comments from anyone? Anything that was not clear so far on the layers? No? Okay, we're about halfway more or less on the presentation. So let me stop here. No questions, no comments. I'm going to pause and see you in 5 minutes. Okay, my dear students, welcome back. I'm going to continue on the lecture here. And I want to look a little bit at the warming of the Earth. It is obvious that the equator is warmer than the poles, right? on our planet Earth, and that also established a lot of the weather system and the weather patterns. And that weather pattern also establishes a lot of the vegetation and therefore also the animals and the ecosystems that live throughout the planet. Just like I was talking earlier when we were looking at the geosphere, remember the different biomes and how different they are. Let's say a tropical rainforest from a coniferous forest, tropical rainforest being at or near the equator and very warm, whereas a coniferous forest being mostly in the northern hemisphere, but very close to the pole itself, to the Arctic Circle, where the climate is very different. And the adaptation of those plants is a radical adaptation to that kind of climate, where it's cold, icy, and very different type of weather than near the tropics, okay? So some common misconception is that why is it, we can ask the question, why is it that it's warmer on the equator and colder in the poles and somewhat in between temperature in between the equator and the poles, right? Whether we go north or south on this sphere. Many people have the misconception that it's warmer at the equator simply because the Earth is a sphere. And if we think of the sphere of the Earth, right? Obviously the equator is closer to the sun, being the sphere, the equator is in the middle. So the equator is closer to the sun than the poles. And the poles being further away from the sun, then is colder. But that's a very erroneous misconception, and we need to clear that up because it's not really the way it happens. That's not the reason why it's warmer on the equator and colder in the polar regions, not at all right? And that difference in temperature is significant enough to have obviously liquid water around the equator and actually ice, the poles themselves, whether it's the Arctic Circle or Antarctica, in ice that is holding a significant amount of water on Earth so that the surface of the Earth or the sea level is at the current level precisely because of those two huge masses of ice, whether it's in the North Pole or the South Pole, okay? So this is not an irrelevant question. The issue about the temperature on Earth and the temperature gradient on Earth. All right, first, let's look at this. It's not about the fact that the poles are closer, that the equator is closer to the sun than the poles. Not at all. And let me give you a little comparison here to scale, all right? If the sun were this big, represented by this red semicircle, if the sun were this big, to scale, the Earth would be about this big, this little blue dot here, all right? And actually a little smaller, I just couldn't get the dot, that circle small enough, but this would be more or less the proportion of the size of the sun compared to the size of the Earth, the two spheres. So you can see then that the distance between the equator to the sun is not significantly different than the distance of the poles to the sun. You follow me? That's number one, just by sheer size and proportion. But even more important than that is that the actual distance between the sun and the Earth is not this distance here. This is not to scale. The spheres are to scale, but the distance is not to scale. If we were this close to the sun, we would just be burnt up. We would be a ball of fire, all right? We could not tolerate this kind of distance to the sun, this closeness to the sun and the sun's heat. No, the distance from the Earth to the sun, again, if the sun were this large, red sphere, And if the Earth was this tiny little blue dot here, the actual distance would be more or less the distance of this dot right here on my screen in this classroom, all the way out to the entrance, the gate of the university, the entrance, which is close to 5 blocks away because we're near 32nd Avenue here, right? The School of Science, the science building is near 32nd Avenue, and the entrance to the university is on 37th Avenue. So if the Earth were this small, the sun would be about 5 blocks away. Look at it that way, 5 street blocks away, all right? And so you can see that at that kind of distance, it doesn't really, the difference between the equator and the poles, the difference of distance between the equator and the poles is absolutely negligible, all right? It doesn't account for the difference in temperature between the equator and the poles. So what does then? What does is a very, very different argument. And this is truly what happens. It has to do with what is known as the angle of incidence. The angle of incidence of the sun rays to the surface of the Earth, all right? The angle of incidence. So this is how the angle of incidence is measured. Let's look at any one of these three letters, A or alpha, represents angles of incidence in 3 different angles. This one, this one, and this one, all right? So the angle of incidence is the hypothetical angle measured in degrees, right? That is produced, that is the result of the sun ray hitting the surface of the Earth and a hypothetical tangent to that spot where the sun ray is touching the surface of the Earth. Now, a tangent, by definition, is a line that touches the circumference at only one point, and at one geometrical point, all right? So let's think about this again. Any circle, the outer edge of a circle is known as a circumference. We can project the sphere of the Earth on a plane. Let's say the board here or the screen is the plane where we are projecting the sphere of the Earth so that we get a 2-dimensional circle, a flat circle, all right? This is the perimeter of the Earth, also known as the circumference. So a line, a hypothetical line, straight line that touches that circumference at a single point is known as a tangent, all right? All right, so now, and therefore, a perpendicular line, a line that is perpendicular tangent, is always going to be at 90 degrees, and it's always going to be like a ray that is coming out of the Earth or whatever other planetary body we're talking about, all right? So a perpendicular line to the tangent, which by definition is at 90 degrees, is going to be essentially like a line of gravity, if you will, going in toward the center of the Earth and going out, expanding radially into the universe, all right? All right, so you know what a tangent is now. The sun rays coming into the Earth through the atmosphere, that light, that photon, when it hits the surface of the Earth, okay, it's coming in at a particular angle. And if we draw a tangent, a hypothetical tangent, where that photon is hitting the surface, the smaller angle, the inner angle, is called the angle of incidence and can be measured. That can be measured. Okay? So another thing that we need to understand here, that for the purpose of the argument being what is causing the equator to be hot and the poles to be cold, or what is causing the temperature gradient on the surface of the earth, right? What is causing the temperature gradient so that as we go away from the equators, it gets colder, either going to the North Pole or to the South Pole. What is causing that gradient? I'm telling you, it's the angle of incidence of the sun rays. But also we have to make this assumption. Because the scale is this kind of scale, whereby if the surface of the earth or the sphere of the earth were this big, this kind of sphere, the sun in proportion would be practically vertical, all right? So if we were to close in here, for example, and just look at this area, this surface of the sun, if we were to project the circle of the earth on the sphere of the sun, that area there would be considered for all practical purposes a vertical, like a wall, vertical wall. What I'm trying to say by this is that the sun rays that hit the surface of the earth for practical purposes are coming in parallel. The sun rays are coming in parallel. Again, because that surface in proportion is so tiny compared to the total surface of the sun. The proportion of the surface of the earth is so tiny in comparison to the whole surface of the sun that for practical purposes, the sun rays coming into the earth are essentially can be considered to be coming in parallel to each other, all right? If that's true, then the only thing that is changing the angle of incidence is the surface, is the curvature of the earth itself. That is what is changing the angle of incidence, is the actual curvature of the earth. Because if the sun rays are coming in all parallel to each other, all right? Then at the equator, those sun rays are coming in essentially perpendicular to the tangent, all right? And therefore is going to describe a short distance. Those sun rays that are coming in are going to describe a small distance, a small area, are going to, let's say, illuminate a small area. But if we have the same amount of rays, or the same number of rays, if you will, or the same slit, right, of rays coming into a latitude that is away from the equator, that is either north or south. In this case, it's north, right? If it's a latitude that is north of the equator, then that same amount of rays is going to cover a larger area, a larger surface of the earth, a larger surface. It also means that the angle of incidence is a smaller angle. It's more angled. Think of it that way. The same amount of rays are being more angled due to the curvature of the surface of the earth, okay? So the same amount of rays in this diagram is represented as 3. Let's say hypothetically 3 photons parallel to each other are coming onto the earth, and near the equator, they are illuminating a small area. But those same 3 photons, that same quantity of light coming in a latitude away from the equator, either north or south, they're going to illuminate, the same amount of photons are going to illuminate a larger area because there's more curvature. There's a smaller angle of incidence. It's a more steep angle, all right? What does that mean? That the same amount of rays have to be distributed into a larger area. And therefore, when they convert from light to heat, that heat is going to be more dissipated. Per unit area, there's going to be less heat per unit area. There's going to be more heat near the equator per unit area than heat per unit area in latitudes north or south, okay? And that's the whole reason why by the time we get to the poles, that angle of incidence is so steep that the same amount of sun rays are covering a much larger region of the Earth, a much larger area. And therefore, when there is a transformation from light to heat, that heat is more dissipated now over a larger surface, and therefore causing less heat, heating less the surface. And the difference is quite significant. The difference allows for the possibility of actually having ice on the poles. In other words, that the temperature will become so low that it could go below freezing, below 0 degrees centigrade, and therefore freezing that water that is there at the poles or near the poles, all right? And therefore containing that water in ice, okay? So that is what causes the difference in temperature, basically, on the surface of the Earth, is the angle of incidence of the sun rays, which are much more condensed near the equator and more dissipated toward the poles because of the curvature of the Earth, of the planet, and therefore cooler on the poles, near the poles, than the equator. All right, now, what happens then is we get this type of effect on the sphere of the planet near the equator, and here the Earth tilt has been taken away, so the Earth has been put rather vertical and horizontal, so there's no tilt in this diagram. Keep in mind, there's no tilt in this diagram of, so it's been simplified, the diagram. The north, the axis, north to south, has been put vertical artificially. We know that there is a tilt of the Earth, but now for the purpose of simplicity, it's put like this, vertical, which means that the equator is horizontal, and that is the warm region represented by this fade red swath here at the equator is warmer at the equators. Colder, represented by blue at both poles. Okay, what happens then is a similar process of the convection currents that we talked about for the geosphere, for the mantle, the convection current where heat rises. So warm air, I mean, remember, it's a fluid, right? It's a fluid that as that fluid moves along the surface of the Earth, the atmosphere, toward the equator, it warms up and it rises, heat rises. As it goes into the stratosphere, it cools, right? We saw that temperature decline toward the stratosphere. As it cools, then it displaces toward the poles, right? And at the poles, it cools further, so it drops. Talking about the air, the atmosphere, and this is the tropospheric air, all right? The layer in the troposphere. So when it reaches near the poles, that air cools, becomes more dense and drops toward the surface. Of course, it doesn't go below the surface of the Earth. It crawls, if you will, along the surface of the Earth. until it starts going through the temperate region and into the warm region, and then warms up again through dissipation of heat from the surface of the Earth, and then will move out back toward the poles and do that circulating pattern, which is a convection current by itself, just by itself, without adding the extra complexity of the spin of the Earth, all right? This is if the Earth was just still, not spinning. These are convection currents, and it happens both in the northern hemisphere and the southern hemisphere, because we're talking about a sphere. All right, so that's just straight up convection. But it turns out the system is not as simple as that. The system is more complicated because the Earth is rotating, it's spinning on its axis, right? And therefore, that spinning motion also deflects the air in a particular direction, which is generally east to west, as you can see here, right? This pattern of east to west, simply because the rotation of the Earth, if we see the rotation of the Earth from the North Pole looking down, we'd see it clockwise. If we look from the south looking up, we'd see it counterclockwise. All right, so these are the patterns that are generated in the wind. And here is another little YouTube to illustrate what is known as the Coriolis effect. Coriolis effect, discovered by this fellow named Coriolis. And it's a twisting, if you will. It's a twisting of the normal convection currents that are occurring simply because of the rising cooling and lowering heating and so forth. Let's look at this for a moment. And you see the pattern here. So these are known as Coriolis currents. Give me a minute. Yeah, okay. Thank you. Bye. Okay. Stop. Start. Volume. Okay, Coriolis effect.
This animation, we're going to look at global wind patterns and talk about the reasons why the air circulates the way it does, and also patterns of rising and sinking air and how that relates to precipitation. The engine that drives it all, I guess you could say, is the intense heating by the sun that occurs only in the equator areas, where the sun is shining at a very high angle of incidence. And this hot air near the equator, being less dense, rises upward. It rises upward and it moves toward the poles, and then it gradually sinks at about 30 degrees north and south latitude. So we create these big spinning circles of air that we call Hadley cells. Now, near the equator, where the air is rising, it loses its ability to hold moisture, and you get up to end of high rainfall and low pressure because there's air leaving the equator. Where the air sinks in these belts at around 30 degrees north and south, you get high pressure sinking air, which creates areas of clear skies and desert climates. Now, as this air circulates and tries to flow back toward the equator along the surface of the Earth, or as some of it heads toward the North Pole or toward the South Pole, the Coriolis effect, the spin of the Earth, causes it to bend and turn, and it's going to create the two big wind belts that prevail on our Earth, 2 out of 3. The trade winds, northeast trade winds and southeast trade winds, and then the prevailing westerlies. Now, these winds curve in the way they do because of the Coriolis effect. Winds curve to the right of their path north of the equator. They curve to the left of their path south of the equator, and they end up flowing from east to west or from west to east. Now, the other big factor is what's happening at the poles. At the poles, the air is cold, and the cold air wants to sink. And as that cold polar air sinks, it heads toward the equator, and it bumps into this air heading toward the pole here and toward the south pole here. And it creates an area of rising air, and again, rising air produces high precipitation belts at about 60 degrees north and about 60 degrees south latitude. At the poles themselves, the precipitation is quite modest because the air is sinking and that creates low precipitation.
Okay. So you see the picture? We have a dynamic system of essentially two main forces going on. One force which is, we can say, vertical or perpendicular to the surface of the Earth as a sphere, and that is going to be the convection current, right? Of warm air rising and cold air sinking and creating that circular motion in the northern hemisphere and the southern hemispheres. But it's only halfway, so this is also a simplistic model in that sense that actually there are two convection currents going on here from the equator to latitude 30, more or less, and then another belt from 30 to 60 latitude, 60 degrees. Of course, the pole is at 90 degrees, right? On either side, 90 degrees north or 90 degrees south. All right, so that's the first force, which is a vertical force, like I say, moving vertically from the surface of the Earth. The other force acting on the weather pattern is a diagonal force because of the spin, because of the rotation of the Earth. And so that diagonal force, which is the angle is smaller at the poles, of course, because it's near the axis, and that angle increases. So it's a curvature. It's not a straight line. It's a curvature because as we go from the poles to the equator, then we're getting on the surface of the sphere, we're getting away from the axis, and therefore it's a curvature that kind of mimics the curvature of the Earth itself, all right? That one, known as the Coriolis effect, then that bends, swirls, if you will, these other convection currents that are going on the wind pattern, thus generating the more realistic picture of the cells that he called the Hadley cells, again, named after Mr. Hadley, who discovered them, all right? And they're essentially three patterns, three wind patterns in each hemisphere. So there's the northern hemisphere north of the equator, there's a southern hemisphere south of the equator, and these three patterns occur north and south. So the first pattern from 0 to 30 degrees north is known as the trade winds, the northern trade winds. You get the same pattern, but in an opposite direction of flow in the southern hemisphere, the southern trade winds, okay? Then there's a transitional region from 30 to 60 degree latitude. The wind pattern kind of reverses because of the flow. Again, the combination between convection and Coriolis, you get what is known as the westerlies, because the westerlies means that the wind is blowing from the west, it's coming from the west toward the east, all right? And you get the northern westerlies and the southern westerlies. Notice that the southern westerlies, the wind is also coming from the west, right? Because it's in the opposite direction of the north. And then finally, you get the polar weather, if you will, whether it's North Pole or South Pole, and generally they are clear skies because, again, the poles being cold, the air being dense is sinking toward the poles, right? And thus displacing what possible humidity or bad weather could be there. Follow? And so cold air sinks, high density, right? High pressure, displacing whatever humidity is there that would cause precipitation or snowing, etc. And that occurs both in the North Pole and the South Pole, again, because of the colder region there, the colder surface of the Earth. Another one last little bit of tidbit of interest, why these are called trade winds is because most of the trade back when shipping was done by sail, right? most of the trade was done here in the region, 30 degrees north to 30 degrees south. If you project this across the globe, North and Central America would be here, and Northern South America, Caribbean and all that. And if we project it, as you can see here, you know, for example, here's Mexico, here's Central America, here's the northern part of South America. In the region between 30 degrees north and 30 degrees south. And if you project that around the globe, you're going to get Europe and Northern Africa on the other side. So basically the Mediterranean, and then even tropical East Asia and all that. So anyway, that was where most of the trade was going on back centuries ago, when trade was being done by sailboats, by sailing ships. And so they would take advantage of the trade winds that were pushing generally from Europe or Africa toward North or South America, generally, okay? And then to go back, they would get into the westerlies, to go back west, to go back home, whether it's in the Northern Hemisphere to Europe or back to Africa in the Southern Hemisphere. All right. Now, a little bit about the Coriolis effect, because it also makes a difference whether one is at the equator or one is at the poles. There are different speeds because of the distance away from the axis, all right? Away from the axis or closer to the axis of the Earth, which would be across the poles here. The geographic, what is known as the geographic pole, different from the magnetic pole somewhat, but essentially at 90 degrees north or south from the equator. Another little video just to show Coriolis, to demonstrate what this is about. Let's see where we're at, here we go. Okay, this one starts right away, so no ads. Here we go.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well. And when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center or eye of a storm is constantly rushing toward the low pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Okay, so you can see that this Coriolis effect of the spinning of the Earth is going to make a differential or a gradient, and whether we are at the equator or closer to the equator, or at the poles or closer to the poles, simply because we're dealing with a sphere, and therefore the distance traveled near the axis is a shorter distance than the distance traveled at or near the equator for the same amount of time. And so that's why she's saying that the equator, any object or anyone on the equator is moving faster in relation to someone or something close to the poles, all right? We can get, then she mentioned very briefly this conserved momentum. Conserved momentum is illustrated here with a figure skater as she is rotating, right? She will get on the tip of that skate, right? These are ice skates. And so she'll get on the tip of the skate and she will be rotating in one direction or the other, depending on what motion she moved to when she got into this rotating pattern. If she moves her arms and legs in, then she will go faster. And that's what's represented here by the hair, okay? The hair flies out because she will move faster if she brings in her hands and her leg because of the conserved momentum. The overall momentum has to be the same, which is a composite of speed and distance, right? The mass that is moving, that is rotating, has to maintain the overall momentum. And so if that mass moves in, then the object, the person in this case, will rotate faster, right? This is just a little illustration of what is meant by conserved spinning momentum. And that's what's making those hurricanes spinning faster at the center, at the eye, than, or near the eye itself, right? As opposed to further out from the eye of the hurricane. And then the rotation, which has to do with the Coriolis effect, again, spinning clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Now, finally, the most important thing here is I want to get to these patterns that was mentioned earlier, one of the other one of the videos, Hadley cells. So we come up with these 3 sets of Hadley cells in the northern hemisphere and 3 in the southern hemisphere. There are the Hadley cells that correspond to the trade winds, the Hadley cell that belongs to the westerlies, and then finally the tropical, the polar Hadley cells that are around the pole, north or south. Okay? And these are the overall wind patterns at the global scale for our atmosphere, for the Earth's atmosphere, these wind patterns. Okay? And this is essentially what is going to determine the weather on any particular day at any particular location. How these cells are moving around in that dynamic system. At the global level, when we look at it at the local level, it depends where we are in those cells, what time of day, what time of night, and so forth. What is the dynamic combination of temperature, pressure, humidity. Those are the three main factors that cause the local weather to be whatever it's going to be, from a very clear sky at high pressure to a thunderstorm at a low pressure system in the middle of the summer. Okay. All right, so that's what's causing weather on our planet. And I just want to kind of wrap it up at the end with the distinction between weather and climate, right? Because notice that the hot topic today is not weather change. It's ridiculous to talk about weather change because the weather is changing all the time, right? The weather is changing all the time. For example, the weather changes on a daily basis from day and night. It's something so obvious that we don't even think about it. During the day, it's light. There are photons bouncing around, gazillion of photons, all right, and there's illumination. At night, very few, so that our eyes normally don't perceive light, especially when it's like a moonless night or something like that, it's dark. So that's the first big difference in weather on a daily basis is between day and night. Now, translate that into the biosphere as such, you know, it makes a big difference whether there's light or darkness on the surface of the earth, beginning with the plants directly because of photosynthesis. Okay, and also that's also why I talked about biomes and I talked about the food chain and the food web and the food pyramid, because whether photosynthesis is occurring or not will make a big difference, not only for the producers, but also for the primary consumers, the herbivores. And since they are affected by that cycle of photosynthesis or not, or essentially plant material available, then also the omnivores, which feed on the herbivores, and the carnivores that feed on the omnivores, etc. The whole web is influenced this way. So we know that weather does have definitely an effect on life on Earth, strikingly on the food, but also other behaviors like mating, etc., hunting behaviors, foraging, and so forth. So beginning with the most obvious weather difference on a daily basis between light and darkness. Also associated with that will be the amount of humidity that is available and the amount of rainfall and so forth. So these are all weather conditions that affect life on Earth, okay? And that is changing, again, on a daily basis. So the standard for weather is to be in a dynamic change, and no one thinks that that is a crisis necessarily, unless there is something drastic, dramatic, like a hurricane or a thunderstorm coming our way. Very different from climate, because climate is long-term, right? We don't talk about daily climate, we talk about daily weather. We don't even talk about monthly climate or yearly climate. Is really stretching it, all right? Because climate is measured typically in millions of years. And if we really want to get picky, we can talk about climate in the order of thousands or tens of thousands or hundreds of thousands of years, but not short term, even seasonal. For example, in a whole year, there could be weather change, say in the temperate region. The tropics are pretty much hot all year round, right? And the weather difference there may be just between wet and dry, which ironically can actually invert the temperature gradient, so that I'm talking about the tropics here, the band that is more reddish, right? Representing heat, more heat year round. We don't have the seasons typically in the tropic or subtropical region as dramatic as in the temperate region. So what happens? Typically the weather change, if we want to talk about seasonal change in the tropics, we may talk about wet or dry season, the rainy season or the dry season, which may actually invert the temperature pattern such that during the summer, which would be the wet season, in the tropics and subtropics, it's actually, because it's more rainy and rain water absorbs heat, it may actually be cooler during the rainy season than in the dry season, particularly deep in the tropics, because in the dry season, the sun rays are hitting unencumbered, there is less humidity, and therefore more heat during the day and cooler at night, okay? So we may have this phenomenon of an actual temperature inversion whereby in some places in the tropics, it will actually be cooler during the day in the summer and colder and warmer in the winter, what we call winter season in the tropics because of less humidity. Different from the temperate region, where we have, let's say we transition into between the 30s and the 60 degrees latitude there. We have what is known the temperate region. In the temperate region, we have pretty much the 4 seasons and the temperature gradient that varies pretty much from solid to liquid water, right? Liquid water being rain, solid water being snow. And we have about 3 months of each season there. Summer, fall, spring, summer, fall, winter, spring, okay? With the temperature range fluctuation, that's where we get the greatest fluctuation of temperature and the greatest variety of weather on a yearly basis. Up to a year, the 4 seasons, what we call the 4 seasons, which in the temperate region, again, between the 30s and the 60s latitude, is more dramatic, the weather pattern because of the 4 seasons, right? Then as we move from around 60 degrees to the 90 degrees, okay, you notice we're at a different Hadley cell now. So we're away from the temperate Hadley. We're now into the more polar Hadley cells. It's more cold year round, typically maintaining freezing temperatures and therefore ice, okay? And we don't see a phenomena of the tropical rainstorms, for example, or even the temperate rainstorms that can happen in the lower latitudes. Okay, so we can see, again, the temperature gradient and the wind patterns will generate different types of weather along the surface of the Earth at the same time, different weather at the same time in different parts of the world, different geographical regions. And all that within a year or the following year or the following year or the following year. So when we are comparing, for example, one summer to another, and we say, well, it's definitely, it was hotter this summer. Let's say the summer of 2020 was hotter than the summer of 2019, all right? And it looks like the summer of 2021 is going to be hotter than last year's summer. We're still within the range of weather. We're definitely within the range of weather, okay? Now, when that temperature increase, for example, continues unabated year after year after year into the decades and into the centuries, then we are transitioning into climate. And it is only then that we can talk about climate change, all right? Because up until that point, it has been change of weather, which is expected because it's a dynamic system, very dynamic system. It's the most dynamic one because we're dealing with gases. See, as we go through the 3 states of matter, the most dynamic by way of fluidity is obviously the gas, then intermediate is liquid, and solid, we expect solids to change less, to be less dynamic in their fluidity, right? So when we talk about climate change, we really are talking longer term. And how do we measure that? Because we can say maybe we've been measuring the temperature of the Earth, for example, we could talk about global warming, right? Talk about global warming, how long have we been measuring the temperature of the Earth with actual thermometers consistently, scientifically, right? In particular parts of the world, maybe just a few centuries. I don't know how far the thermometer goes, really. It's very interesting to find that out. But the point is that we only go back really centuries with measuring the temperature of the Earth in different parts. And even that has not been that consistent. I would say consistent probably 200-300 years at most, okay? Which kind of matches up with the Industrial Revolution of using fossil fuels, burning fossil fuel in large amounts, precisely for the machinery of industry, mass production of, yes, goods, the stuff that we get, all right? The stuff that we keep accumulating that is mass produced requires a lot of energy, typically electricity, to run all that machinery. And therefore, since traditionally that electricity was being generated by burning coal or petroleum or even natural gas, then the exhaust of that is, of course, CO2. CO2, burning fossil fuels, and we go back to that 400 ppm of CO2 density right now in our atmosphere, okay? So that's kind of going full circle, but it's still on climate change, whether yes, there is climate change, but what is the anthropogenic component of that climate change is still debatable, simply because we don't have such a large time frame, a scale of time that has transitioned. But there we see all indicators pointing toward, yes, a warming of the Earth, that correlates, and I'll show you some graphs later in the course, actually graphs that I developed with the course in statistics, biostatistics that you're taking now, the statistical methods a few years back in the first cohort of the program. Okay, we'll look at that evidence later on toward the end of the course. Okay, so anyway, we understand, since we're talking about weather, it's talking about the atmosphere and weather patterns. Now you know a little bit about how those weather patterns are generated, at least at the global level, the general weather patterns. Then it, of course, depends where we are locally, what kind of local weather we're going to be having that particular day or night. And the transition from weather to climate, which is a long-term thing. So these records are very, very important. And then we depend on what? We depend on what is known as modeling. In other words, statistical approximations, right? We crunch in the data that we have been accumulating so far over decades and centuries and even millennia, as in this graph here. We're going to revisit this graph later in the course, but since I brought it up already, obviously, we did not have thermometers back 100,000 years ago to be measuring this temperature, all right? And we did not have CO2 gauges either to be measuring the ppm of CO2 back 800,000 years ago. No way. And so how do we determine this? Indirectly, mostly by ice cores. Ice cores, yes, drilled in the Arctic or Antarctica, through the ice, layers of ice, and then the CO2 gas that is trapped in there, little tiny, even microscopic bubbles or minuscule bubbles of CO2, then we can measure the ppm going back quite a few thousand and even hundreds of thousands of years. But it's indirect measure, and therefore there's a larger margin of error, right? Okay. Well, I think that's about it now. Well, the last slide, obviously, a natural right to clean air, because each one of these I want to finish with something related to the human itself. Just like, well, I think I forgot to mention in the geosphere, we have a natural right to live somewhere on Earth. And that is already a challenge, because no matter where we live on Earth, we're going to cause a footprint, right? We don't live up in thin air. And that footprint, by necessity, is going to have to clear out some of the ground, some of the other species that were living there before. So when we put our house or condominium or wherever we're going to live, that is going to displace locally that other ecosystem that was there before we got there. But we have to live somewhere, and we have a natural right to live somewhere on Earth. We should do it in a eco-friendly way, right? So that, excuse me, to try to reduce our footprint as much as possible, but we have to have some kind of footprint. The same with the atmosphere. We have a natural right to clean air because we need to breathe to stay alive. And this is before positive rights or civil rights, okay? I mentioned this because a few years ago in the news, there was this news that Spain was taxing people for the air where they were living. And it was odd, it was very strange. They were trying to raise some kind of tax that had to do with using the atmosphere above the place where people were living. So I guess somehow the government of Spain was claiming not only the surface of the earth, but also the air above that surface that belonged to them. I guess in a sense, you know, we have, for example, flight patterns, and we have a right to certain territory. What is that called? Airspace, the airspace, national airspace, right? It belongs to the particular nation. So flights and airplanes from other parts of the world, from other nations, need a permission to fly above the national airspace of each country. All right, and then there's airspace that belongs to all the nations, for example, above the oceans mostly, the vast expanse of airspace there. But above nations, kind of vertically from the nation up, it does belong to, it's mostly for security and safety reasons, right? Somehow Spain was trying to tax the people for the air above their ground. And I don't think it went very well with that idea. But basically we have a natural right to clean air because we need to breathe. And so the issue of contamination and pollution, we can make an argument against pollution and against the industries that are polluting because we have a natural right to clean air. All right, and therefore the government who represents the people has a right to tax this industry and to actually regulate industry so that they don't pollute the air that we breathe. Okay, gonna leave it at that. It's around noontime, so questions, comments, anything? Everybody on board? Okay, well, if there are no questions or comments, then I'm going to close it here. And we'll meet up again next Saturday, and it will be the hydrosphere. Well, yes, I made a little change. This is an updated PowerPoint on the atmosphere. Basically, sorry, these two slides here. All right, let me see. These two slides on the chemical composition of the atmosphere and zeroing in on the CO2 parts per million in anticipation of talking about global warming and climate change later on in the course. So this is I'll email you this. I think I emailed it already, but I'll include it in the email of the link to the video. Okay, folks, thanks again, and see you next week.
Thank you.
All right, all the best.
Bye.
Bye.